my name is Arash Pouryazdan. I'm from the Sensor Technology Research Centre at the University of Sussex, UK. Do accept my apologies for not being available to present this work in person at the conference. Today I'm going to talk about the research we conducted on long-range, non-contact AC voltage measurements. So we're going to start with motivating the work, and then we're going to talk about the principle of operation of this non-contact voltmeter. Then we're going to talk about the electrical potential sensor, which is the technology used to realize this device. And then we're going to move on to our calibration methods and discuss some of the results that we obtained using this device. This voltmeter has three modes of operation: fixed distance, variable distance, and frequency measurement. So fixed distance is when you keep the distance between the voltmeter and the source on the test fixed. Variable distance is where you can move the device back and forth freely and still be able to measure the voltage. And frequency measurement is self-explanatory. You measure the frequency of the source. So why do we need a non-contact voltmeter? So there are cases that the terminals of a source on the test are inaccessible. So they are either insulated or they are encapsulated, so we can't touch them. But there are also cases that, due to the high voltages in a system, it's simply not safe to go in with conventional resistive probes and just touch tens of kilovolts with normal multimeters. So let's say power grids. So how does this work? We use an electrometer sensor, we'll talk about this later in the next slide, to measure the electric potential. So the electric potential at a fixed distance varies linearly with the source voltage. Now, if you start to move the device, i.e. change the distance, you add a second variable because the electric potential also changes with distance. So at a fixed distance, you can calibrate the device for different source voltages and use it. For variable distances, you need to know the distance. So in this case, we use rangefinder sensors, and then from there, we can calculate the source voltage by having both the electric potential and the distance from the source. So in this graph down here, you can see that for a 240 volts RMS source, different distances, the measured amplitude has decreased. So at 10 centimeter, we measured almost 2 volts, and then we go down at 30 centimeters and 50 centimeters, and so on. So the technology that we used, we called it electric potential sensor. That is a technology developed and patented here at Sussex. It's a type of capacitive sensor, and you can think of it as a near perfect voltmeter where there's no current drawn or no conduction current is drawn from your device. So we only measure displacement current. It can measure electric potential and electric field. This particular IC that we used has 20 gigaohms of input resistance and 15 picofarad of input capacitance. These values are achieved by use of positive feedback. But we have also developed devices and sensors with teraohms of input resistance and attofarads of input capacitance, but this device was simply good enough for this application, so we went with the commercial version of our technology. And this particular IC has 20 kilohertz of bandwidth, and it has plus minus 5 watts of dynamic range. Its sensing electrode is also built in to the IC itself, so that's the area you can see here. So here's a block diagram of our non-contact voltmeter system. So it starts with the electric potential sensor and its sensing electrode. The dotted area around the sensor is a screening box connected to the ground of the circuit. So we use this box to make the sensor more sensitive to only fields, or only sensitive to fields in front of the device and nothing in the sides and behind of it. The output of the sensor is then high-pass filtered to remove some of the artifacts from movement, and then it's amplified and low-pass filtered to remove some high-frequency noise, and then it's level shifted and digitized using the 16-bit built-in ADC of our microcontroller. The microcontroller is responsible for calculating the source voltage, basically holds the calibration information, and displaying the actual voltage. It's got some controls to control the operation mode. It's also connected to a speaker so that we can use the speaker as means of feedback, audio feedback to all their people from live voltages or setting a threshold and alerting them that they've exceeded this threshold. The microcontroller also receives data from 2 time-of-flight infrared laser sensors. These sensors are used as rangefinders. The reason we use 2 is because one is optimized for long distances, anywhere between 15 centimeters to 1.2 meters, and the other one is used and optimized for low distances, so anywhere between 5 millimeter to 150 millimeters. So here we've got a picture of the device, inside of the device. Again, we have our 2 infrared time-of-flight sensors commercially available, and in the middle we have our electric potential IC that's mounted. The screen box is not shown in this picture, but then it's just mounted around to surround this sensor. In the right hand side we show the conditioning circuits, some op-amps and filtering, and then here's the speaker that we've used. It's been taken from an old laptop, been upcycled. And then we've got a microcontroller here, it's 18Z3.2, plus some charging circuitry and our battery. So this system is completely battery operated and it's not connected to any mains supply. So as I explained, in the fixed distance mode, the device is kept, the distance between the device and the source is kept constant. So here you can see by means of 2 PCB spaces, nylon spaces, we kept the distance fixed, but it is still a non-contact measurement because there's no conductive path for current to travel through. So in the left hand side, you can see that we varied the source using a variable transformer, and we recorded the ADC output values for each different source voltage. And then from there, we fit a line into this data. You can see it's pretty linear, and we use this equation as a calibration equation. So in the right hand side, we have run a new measurement where we again change the source voltage from 25 to 250 volt RMS, and then we recorded what our calibrated voltmeter is giving us. And as you can see, we've achieved plus minus 1.4% accuracy. Again, pretty linear. That's not surprising. And it's been calibrated for source voltages between 25 to 250 volts. So here, the device is used in variable distance mode. So we've used the infrared time-of-flight sensors to measure the distance, and we also use the electrometer to measure the potential. So because we have 2 variables, we end up with a calibration curve that is in 3D. So we kept the distance fixed, let's say at 100 millimeter, and then we varied our source voltage, and we recorded the ADC values. As you can see, the source voltage varies linearly with the ADC value, but then the distance has this curve, 1 over D curve, with the measured voltage. So from this point, we've calibrated the device, so we obtained multiple lines similar to the one on the previous slide for the fixed distance. For each distance, from this point on, the microcontroller receives the distance data from the rangefinder sensors, and depending on what reading you have, it applies a specific calibration line, and it calculates the source voltage. So we've done a new set of data here for source voltages of 250 volts, 200 volts, 150 volts, 100 volts and 50 volts. So as you can see, what is immediately apparent that at low distances and large voltages, so this area here on the graph, you have higher errors. One of the reasons for that is that the sensors are not very accurate at low distances, and at short distances rather, and also the strength of the field is very large, the electric field at low distances from the source, so small movements of the device will really affect the accuracy. And this device was calibrated for distances between 50 millimeters to 600 millimeters, and source voltages between 25 to 250 volt RMS, and we achieved an accuracy of plus minus 5 volt RMS. Most of the inaccuracy comes from the rangefinder sensors, as it was apparent in the previous slide. So for the frequency measurements, it was a pretty trivial measurement at this point. You have the waveform in your microcontroller. It's very low frequency, 50 Hz, 60 Hz, 50 here in the UK. So you might as well measure the frequency as well. So we've used a function generator as a source, and we varied the frequency, and we measured the frequency and calibrated the device using the microcontroller. So the accuracy that we achieved was 10 millihertz. That's pretty much down to the crystal of the microcontroller, the clock of the microcontroller. And we calibrated it for, or we characterized it rather, for frequencies between 5 Hz to 500 Hz. So in summary, we presented a non-contact AC voltmeter with 60 centimeters of range. At a fixed distance of 25 millimeters, we achieved a plus minus 1.4% of accuracy. At a variable distance, the accuracy was reduced to plus minus 5 volts RMS, and that comes from the lack of precision in the time of flight infrared rangefinder sensors. In the future, we plan to add phase measurements by having a second sensor that is synchronized to this one over Bluetooth or some other wireless protocol to measure the phase. So we have amplitude, frequency, adding phase would complete the whole. And we are planning to add auto calibration to this, and also we would like to improve the accuracy by finding more accurate distance sensors or rangefinder sensors. Thank you for listening, and I'm open to have any of your questions.